All right, and part of this, think of it as a review for the exam in 2 weeks. So these are some of the questions. I can ask a lot of questions, actually. All right, so actually, I had some questions here. Yeah, all right. So these just in the few minutes here, these are types of questions I can ask on the exam, right? So for instance, I can ask you, um, what is a certificate? And why are certificates needed in public key cryptography? So that's something that you really need to. I haven't really addressed this yet, but this is something that drives the next question. So that tie it to something called VeriSign, a company called VeriSign. That's really important. Okay, so the companies or people who place their digital signatures on certificates are called what? So they're called certificate authorities. This is something else that we're going to discuss. What is the Diffie-Hellman algorithm for exchanging a secret session key? So you know that now. What is the difficulty of breaking the RSA cipher? Factorizing large prime numbers. Okay, so those are some of the questions that, so there's a lot of questions that I can ask, okay? So I'll be trying out some of those on the exam. All right, so let's now go ahead and go back to Brightspace. Okay, so we are recording, sharing the screen. So we've got Brightspace here. This week, we are working on certificate authorities and digital signatures. Actually, before I forget, let's just touch on the project real quick. So we are currently on week 10, and I want to make sure this is assigned to you guys already, right? So you will need to do a term project that you will need to do a presentation and a demo of your term project. That's going to happen the week before finals. Okay. Now, this project does not have to be a massive project. Okay. It's only worth 10% of your grade, but it does have to be related to cryptography. That's the only thing. So in general, look for something that I haven't covered in class, right? So, yeah, so you have to do some slides. For instance, you're explaining an algorithm or explaining a technique. You don't have to code it either, right? It could be a tool that you install as long as it's related to cryptography and it's interesting. But you definitely need to demo something like some software, or you can write a script. So here's, so select a topic. So here's the link I provide. Select a topic related to cryptography of your choosing. You will need to research and present this at the end of the semester. You need to discuss the topic and do a demo. The demo can be based on code or an application, such as in Linux. Don't use Windows. Examples, break a cipher such as RSA or AES. Obviously more robust than what we've done in class. That would be fun. What is quantum ready cryptography? I will provide an example of the Qiskit technique, and I'll do an example of breaking RSA, just like we did FactorDB, but with a quantum computer. I may touch on Shor's algorithm briefly. That's the algorithm implemented on a quantum computer to break RSA. But it'd be interesting if you guys can find, new algorithms that use quantum, or, what are quantum ready algorithms, right? So you can talk about them as well. All right. So just find out what's going on, interesting things. Blockchain and crypto, if you discuss the algorithm. So not about like economics or finance or investing in crypto, that would be outside of scope of the class. But if it is about, how does blockchain work? Although I'll cover a little bit of this, I won't cover so much. So you guys can, certainly talk about blockchain, how it works, how cryptocurrency, specifically, how do you generate those things, how they work. Diffie-Hellman, more information about Diffie-Hellman or similar algorithms. Elliptic curves for cryptography. As I said, I'll cover it briefly, but you can go more in depth into these topics. And then otherwise, other vulnerabilities in cryptography. that you can find. You know, some scenario, maybe there was like a use case, you know, of cryptography that's interesting, something like that. Does that make sense? Or any other ideas? Honestly, this is kind of a list of examples, but you can find other topics as well. So in the past, some students have done like a VPN. If you do that, though, you have to explain how it works, right? With the networking, and there's a demo component. So questions about the project? They can be groups of 3 at most, minimum of 2. And then everyone needs to come up here, present 15 to 20 minutes, take questions, and just make it interesting. Questions? Is that pretty clear for everyone? Sir?
What's the minimum?
Minimum, I mean, just enough to explain what you're doing, 10 slides, but you definitely need to do a demo. So I like it when, don't just do slides, you have to like, okay, here it is, and this is what it does.
So the project is presenting both the topic if I'm interested and demo something related to that.
Yes, exactly. So just an example, let's say that you did elliptic curves, right? So then you have to explain that elliptic curve algorithm, you know, that particular version of it that you're implementing, you know, discuss the main ideas, how it works. And then by the way, here's my secret message, and I'm going to encrypt it with the elliptic curves algorithm. So, you know, here's the 2 prime numbers, they go into the elliptic curve function, I get this, boom, I encrypt, and here's the cipher, and now I'm going to decrypt it, and I get my message back. Yeah, something like that. And as I said, it can be something you code, or it can be a program that you installed on Linux, for instance. All right, no other questions, so that's assigned. Okay, the project is assigned. Form your groups. Maybe I do like to see like a brief demo just before the presentation. So like the week before, I'll sit with everyone and you can just show me, I guess, you know, what you're going to talk about, just so I can give you a little bit of feedback before you do your presentation up here. So the week before finals is just presentation. Okay. All right. So hopefully that's clear. That's assigned. So now let's go back to the slides. So I have a lot of small slides that have been accumulating. So I believe the first one starts here. Or not. We've done those slides. We've done those. So I guess yeah, so I think it's this one. That's the first one. Okay, so let's take a look. Yep, as these, okay, and then there's another one in here. Right. Okay. So these two I want to cover today. Let's start with this one. This one is shorter. And as I said, some of these are just summarizing some of the concepts that we've covered with the slides. Okay, great. All right, so in summary, the RSA, Rivas, Shamir, and Edelman encryption technique. The RSA encryption scheme provides asymmetric public key encryption. The public key, as you know, consists of 2 large integers, e comma n, and the private key consists of two large integers, d comma n. Note that the second number n is the same in both, right? So we've talked about that. The three numbers e, d, n are related in a special way, math, right? Which requires a bit more mathematics, which we've covered already. So that should be clear in your minds. The crucial point is that n is guaranteed to be the product of two prime numbers, n equal p times q, for the two primes p and q, right? So we've covered that. If you know e and n, which you do, and you found the factorization of n into p and q, you can compute d easily, as we have shown already. So the security of RSA requires that factoring a large integer is difficult. So Diffie-Hellman, for instance, has a different thing other than factorization, but I'm just not going to get into that. And as you know, when they say large, they are not kidding, right? Today, RSA implementations might use 4096-bit numbers for n, which we've already seen that as well. This is important. Nobody currently knows how to factor numbers of that size quickly, which is to say before, it takes years to do. So RSA seems pretty secure. However, no one has proved that it's impossible to factor numbers quickly either. So there's no proof. There could be a mathematical proof that just says this can't be done, but there is no such thing. So RSA may be broken someday, or maybe it's already been broken and it's just state secret, right? Right? This kind of summarizes the whole basic problem. If someone's laptop is encrypted, let's build $1 million cluster to crack it. They have 496-bit RSA. They can't do it, so it's might as well just hit them with a wrench that costs $5 until they tell you the password, right? So people can obsess over the other one, but this can be just as effective, and it only costs $5, depending on if you're willing to harm someone or not. It's just some crypto humor, all right? All right, so digital signatures. We've talked about this concept also. So this more formally, I will state it here. And as you know, this is digital signatures. We've only started to discuss, and we will continue to discuss it for this week. So digital signatures. Okay, so suppose what's the use of them, right? So what's the use of them? So suppose Alice sends a contract agreement to Bob, right? So a contract doesn't have to be private or a secret. Contracts can be public, but what's important is that the contract is respected, right? Because that's business and everything. So to avoid legal trouble, we'd like this communication of contracts to have the property of non-repudiation. So remember, I may ask that question on the exam. This relates to the principles of information assurance as it relates to cryptography, right? So in this case of not denying a contract, non-repudiation is the term, the pillar. Bob should be assured that Alice can't back out of the deal by claiming she never sent the contract, right? So we do have a mechanism for that, and that is basically the digital signature. Likewise, we want the property of integrity in here, and also digital signatures achieve that. Why? Because as we established the last time, we take the contract, hash it, and we sign the hash of it, right? So we've established that. So likewise, we want the property of integrity. Alice should be assured that Bob can't modify the contract and claim that the modified version is what Alice sent him. There's a nice technique, which is this one, digital signature, that provides these guarantees. Alice simply computes a hash of the contract agreement, encrypts the hash with her private key, and sends the result, which is the electronic signature along with the contract to Bob. So this is problem 2 of the 2 problems that you're doing for your current homework assignment. Anyone can take the contract, hash it, and compare the result with what you get when you decrypt the electronic signature with Alice's public key, because Alice's public key is available. It's on her Twitter account or her website or something. If it matches, then the contract must be exactly the same as what Alice sent. Because Alice must have sent it, because only Alice can encrypt something that decrypts properly with Alice's public key, right? So that should be clear. The contract can be modified because the hash value would have changed. Got it? All right, so that's pretty important, right? But that takes us to the last piece of this. There's still one more thing, okay? But actually, this relates to the certificate authority. All right, so the man-in-the-middle attack, right? So asymmetric public key encryption is almost magic, right? You create security out of insecurity. However, there's still one weakness in the system. There's one last weakness, okay, in the system that's fundamental. You see on a website something like, hi, I'm Bob and my public key is that one, right? So you see that, this is the E, this is the N. So, okay, we've established that that's a public key. Some website says, hi, I'm Bob, and this is my public key. But how do you know that how do you know that that public key really belongs to the guy you know as Bob? Do you see what I'm saying? Because you get to a website, and in that website, you know Bob, like you know Bob personally, but you don't talk to Bob in this scenario. Instead, you go to a website and you know that's Bob's website, and it says, hi, I'm Bob, and this is my public key. But how do you really know that that's the key of Bob? Because that website could have been hacked, right? Between today and tomorrow, someone can hack the website and go in there and change that public key to some other public key. Do you see that? And then you're going to use that, and you're sending communications that are going to be, as the attack says, it's a man-in-the-middle attack. So they're going to be intercepted along the way. You think you're talking to Bob when, in fact, you're talking to a man in the middle. You see that? So how do you address that final problem? That's addressed with the certificate authority. What that means is that at some point, there is a trusted entity, such as VeriSign, something that is highly regulated by the government. And so it's literally like a person that you trust. So now that certificate authority will have to sign Bob's public key. Do you see that? With the same idea of digital signature. So what is this in this scenario? It is something like a company like VeriSign. So you will go to VeriSign. Bob, in this case, goes to VeriSign. Let's say that VeriSign is in Seattle, but maybe they have an office here in Chicago, right? So you get in your car, you take all the documentation that you have, your company, whatever, you go in person, go to VeriSign, you pay them, and what does VeriSign do? VeriSign will take their private key, sign your public key, right? And then they give you that digital signature. Then everywhere in the world, in your browser and things that you control, like on your laptop and your browser, what do you have in there? VeriSign's public key. So then what happens is they went to VeriSign. VeriSign used their private key to sign the public key of Bob. When you get that public key of Bob, that before you didn't know how to trust it, right? It's going to go into your, let's say, your browser, and in your browser, you have the public key of VeriSign. So when you run it, it's going to verify that, yes, it was in fact signed by VeriSign. So it checks out, and that's how you obtain the final step of security. Do you guys understand that concept? Does that make sense? Are there any questions about that? And that is called a certificate authority. So at the end of the day, the final step is you have to trust someone. You kind of have to trust that entity. And you'll see, we'll do a lab where you guys become a certificate authority. You will sign something with the private key that you generated, and then you'll have to add your public key to your browser so that when you get a public key, your browser will be able to check it and verify that it was in fact signed by your private key. There are, in fact, there are companies that do certificate authorities, and basically every person that has Linux can create their own certificate authority. So, and create what is called a self-signed certificate. Got it, guys? Same principle, but the key thing here is that you trust. Like, that cannot be compromised. Like, if somebody right now, let's say it would take but I imagine they have a lot of security, so it would take like a government, right, to like attack something like VeriSign and compromise them. If that happened, yeah, the whole internet could be compromised. You see that? So that's kind of the idea. Anyway, that's the first introduction to that concept. We will definitely touch on it a little bit more. All right, so let's just read through this because this is probably stated better. So the question was, think of it as a man-in-the-middle attack. How do you know that that public key really belongs to Bob? Well, you can be assured that if you encrypt a message with this key, only the key's owner will be able to decrypt it. How can you be sure that the key's owner is really Bob, right? Instead of a man in the middle that replaced it. So if you trust a website on which the public key is posted, you might be comfortable. But at the end of the day, you have to trust whoever is presenting this key as belonging to Bob. And that trust is a security weakness. But as I've stated, a certificate authority provides that last step. Okay, because it's like a limited thing. Like in the browser, you don't have the billion public keys that are probably available in the world right now. You only have maybe 200 or so public keys in your browser, and those 200 public keys in your browser belong to certificate authorities. VeriSign, pretty sure Google is a security authority, Amazon probably, and other companies, and they pay a lot of money to Firefox, the other browsers, Chrome, right, to put those keys in there. So obviously the browser, it needs to be very secure, but you guys understand this, right? So a browser that's installed, you should not install just any random browser on your computers. You Chrome, Mozilla, those browsers are software that is designed, and there's a lot of security in them because that's how you access your bank, all that stuff. But we'll see a lab in a couple of weeks that will illustrate that concept. Make sense? All right. So hopefully that makes sense. All right. So we have time for some slides. We have about 10 minutes. So we did this slide. All right. So let's go ahead so that one's covered. Hopefully we can finish the other one too. All right. So I covered this one. Yeah. All right, so then I have this other one. Some of these concepts we had already covered, so it's more of a summary. Okay. So remember the principles at this point, we have covered all the principles, okay? Cryptography provides the building blocks to achieve security. We have covered confidentiality, integrity, authentication, non-repudiation with contracts today, and the certificate authority, right? So that was the last one. So remember Bob and Alice. So we're going to look at scenarios, so again, of cryptography. So we're going to summarize. So the fundamental limitation of symmetric secret key encryption is how do two parties agree on a key? So at this point, we have explored at least two techniques, Diffie-Hellman and RSA, for this task. In order for Alice and Bob to communicate securely, they need to agree on a secret key. In order to agree on a secret key, they need to be able to communicate securely. So it's a whole chicken and egg problem. So this problem is especially common in the digital age. We constantly end up at websites with whom we decide we want to communicate securely, like online stores or bank, but with whom there is not really an option to communicate offline, to agree on some kind of a secret key. And fact, it's usually all done automatically, browser to server. And for the browser and server, there's not even a concept of offline. They only exist online. So we need to be able to establish secure communication over an insecure channel. And as you know, symmetric encryption cannot do that. But you know that the solution is asymmetric encryption or the public key infrastructure. In asymmetric public key cryptography, both communication parties, Bob and Alice, have 2 keys of their own. Just to be clear, that's 4 keys total. Each party has their own public key, which they share with the world, and their own private key. So you guys know this. The magic of public key cryptography is that a message encrypted with the public key can only be decrypted with the private key. So Alice will encrypt her message with Bob's public key. And even though Zelda knows she used Bob's public key, and even though Zelda knows Bob's public key herself, she is unable to decrypt the message. Only Bob, using his private key, in this case, can decrypt the message if he's kept it secret, right? So all of this just summarizes a lot of the things that we have discussed. So we had the diagrams, Alice and Bob. So in this case, this one, Alice wants to send a message to Bob, takes the plain text, is going to encrypt it with Bob's public key, create a ciphertext. That ciphertext is sent over the insecure internet. Zelda is going to snoop. Then the ciphertext is going to be received by Bob, who will decrypt it with his private key, right? So, but remember, we can do many things beyond this. This is just a simple concept. There's the authentication option, and then there's the one-shot option that I asked you to do on the homework assignment. So asymmetric public key encryption, it's impossible to overstate the importance of this. Alice and Bob do not need to plan anything ahead of time to communicate securely. In fact, you can go to a website right now that you've never been to, and it'll just work, right? Alice and Bob do not need to plan. They generate their public and private key pairs independently and happily broadcast them to the world at large. Alice can rest assured that only Bob can decrypt the message she sends because she has encrypted it with his public key. So this is very important that you understand these concepts very clearly. All right? Yes, she's received a message only he could read, and the message claims to have been sent by Alice. But he has no guarantee that it really did come from Alice, right? So that's the issue. Some public key cryptography algorithms, including the RSA algorithm, have the special property of being commutative, which means that the roles of private versus public key are interchangeable. Okay? Time is it? We still have 6 minutes. Let's look at all the zippers. All right. So I want to finish these slides so I don't have to come out. All right. So thus Alice could encrypt a message with her private key that is decryptable only with her public key, right? And you know that that achieves authentication, right? Since everyone knows her public key, you may well ask what the point would be. Well, this message would be readable by anyone, but only Alice could have created it. Okay, that's really important because only her private key produces messages decryptable by her public key. So that's the authentication piece. This provides a form of authentication. So if Alice's plain text message is M, and she first encrypts, so this is actually the homework, right? And she first encrypts M with her private key, then with Bob's public key. Bob can take the message he receives and decrypt first with his private key, and then with Alice's public key, and he'll recover M. The guarantees are that only Bob can read the message and only Alice could have sent it. This is literally what you're doing in the problem, right? I said one shot for all 3 things. Do you remember? You know what I mean? Okay, so here is a diagram of this idea. Let's imagine Alice is communicating with Bob, so you can basically take a look at that. You start with a plain text message, a text file, and you're going to encrypt with Alice's private key. So Alice is the only one that can encrypt it with Alice's private key. That achieves what? Authentication or confidentiality? Alice uses her private key to encrypt the plain text. Authentication or confidentiality? Yep, great. Right, that creates cipher 1, some byte array. Then that is encrypted with Bob's public key. What does that achieve? Confidentiality. That creates ciphertext 2, another byte stream. Send it over the insecure internet. Comes in, cipher 2 is decrypted with Bob's private key. What does that achieve? Confidentiality or authentication? What is that related to? Confidentiality. Okay. That creates cipher 1. Cipher 1 decrypted with Alice's public key. What does that achieve? Confidentiality or authentication? Or is related to authentication, right? All right. And then plain text again. So in one shot, you can achieve all of these ideas. Got it? Yeah. All right. Perfect. Yeah. Okay. I guess. I'll let you guys. We'll come back to these. That's fine. All right. I'll stay for. We'll stop here.